Hey folks, welcome to this episode on standard enthalpy of change. So we saw in the previous episode about what a molar enthalpy is, and it's basically looking at the overall enthalpy change. Again, remember what enthalpy is the sum of the potential and the kinetic energies of a system. And so in this case, when we have 2 moles of water reacting with 1 mole of oxygen, we create 2 moles of H2O gas. And here we have 485 kilojoules released, because again, it's released. We know that because it is on the product side. Now we can also add this a different way. We can say our delta H, in this case, would be negative 485 kilojoule, negative because again it's being produced. However, it's much more beneficial to standard as a per mole basis so that we can actually compare things very easily. Now in this case, what we see is that hydrogen and oxygen are combining to form water. And so if we use the definition of the molar enthalpy of formation, which is denoted by delta HF, we can turn this into a per mole basis. So we see that for 2 moles of water being created, we have 485 kilojoules produced. So to get a per mole basis or a molar enthalpy, I can take the moles of whatever the definition is, in this case formation, so it's looking at 1 mole of product being formed. I take this divided by that 2 moles, and I get this value over here. So my delta H of formation is negative 242.5 kilojoules for every mole of water formed. Now again, this X over here, can be changed to help us denote different definitions and different per mole values. So there are a few things that we have to look at in terms of enthalpy changes. It does depend on a whole bunch of different things, the amount of substances, the temperature, and the pressure. And so we try to control for these different things, and we call this the standard enthalpy change, or the standard enthalpy of formation, the standard enthalpy of combustion, etc., etc. Now, with this notation also comes certain parameters that the reactions have to undergo. Now you can see that this standard enthalpy of whatever is denoted by this little knot in the corner. So whenever you see that, it means that the reaction has been measured under these standard conditions. So what are these conditions? These conditions are as follows. So you can see that it's going to be done at room temperature, 25 degrees Celsius, 100 kilopascals, and at constant pressure. 1 molar concentrations if we're using any kind of solutions. They have to be in their standard states at that temperature. So this is a little important point here, that at 25 degrees Celsius, if we looked at hydrogen, for example, we'd expect it to be a gas. Water, we expect it to be a liquid. So that these reactions are done, and the products that are formed are the same products and states that would be formed at standard conditions. Now, sometimes we'll be dealing with unstandard conditions. For example, we might form H2O gas, and not only, so if I formed H2 plus O2 and I got H2O gas, I can also know that this is a physical change, and I can account for the change in energy for water vapor or steam going into liquid. Now this is going to be something that we talk about a little bit later, and there's also a little other note that we have to talk about with regards to standard enthalpy. And again, the last thing is that all of these energy changes are done on a per mole basis, hence the molar enthalpy. So here are our definitions. So depending on what you're looking at, the definition does change. Again, all of these are molar enthalpies, so the enthalpy release or the enthalpy change is going to be done on a per mole basis. However, per mole of what is the question? And so this chart allows us to figure out per mole of what. So if we're looking at the enthalpy of fusion, aka melting, what we're going to be looking at is how much energy, so if this case energy has to be taken in because we're melting, for example. So this is going to be an endothermic process. So how much energy is taken in for every mole of water being turned into a liquid? Same thing with vaporization. So if I take from a liquid to a gas, I vaporize it. It's going to be how much energy is required to turn 1 mole of this compound over here, which is methanol, into a gas state over here. So you can see that this is a physical change, this is a physical change, this is also a physical change, and this is also going to be a physical change here. So regardless of whether or not they're physical changes, we still have to pick a definition basis and do a per mole value on that. Now, this one's an interesting one. When we look at atomization, we take a molecule of chlorine and we want to break them up into individual chlorine atoms. Now, again, I have to make sure that this is a per mole basis of the thing that is defined. The thing that is being defined is the gas product over here. And so I need to make sure that the coefficient in front of that Cl is 1. Now the only way that I can do that, remember that Cl2 is a diatomic molecule, like that. And if I was to have a value of 1 over here, that would mean that I would have to balance and I would get a value of 2 over here. Now that's not possible. So what I'm going to have to do is I'm going to actually have to use a half over here to get a value of 1. So again, the important point of this is to, number one, understand what you're defining, and to also understand that you need to have a coefficient of 1 in front of that item that you are defining. Everything else might be in fractions, might be kind of goofy fractions as well, it might not always be halves, but you can use fractions to achieve the 1 mole of whatever you're measuring there. Formation, again, it's 1 mole of a product formed, so all of this stuff is from its basic elements, and so we need 1 mole over here. For combustion, it is going to be 1 mole of fuel burnt, and everything else will be fractions as necessary to get that 1 mole over here. These 1, 2, and 3 are all chemical. So going through this just very, very quickly, fusion is generally used in the same format if we're talking about melting or freezing. The only difference, in this case, we have melting over here, same FUS, and freezing, we still have the same FUS. Now, some places will actually have a different one. You might see FRE in over here, or you see MELT instead of fusion. So you might see some different things depending on the textbooks or lessons that you learn. But they mean very much either going from solid to liquid or liquid to solid. The difference, however, how do we know this is the case? Again, it is this sign of the value here. So positive means that this is an endothermic process. Again, this is a physical process because we're just changing states. This is an endothermic process because we're adding energy, we're adding heat into this, and we're increasing the enthalpy of these compounds or these atoms over here. So to go from solid to liquid, you're going to be increasing kinetic energy in between between these two different atoms. Over here, because we are changing our enthalpy, going from a liquid to a solid, there's a lot less kinetic energy in a solid than there is in a liquid. So that kinetic energy is going to be transferred and transformed into heat. And so heat is going to be lost as shown by that negative in front of there. So again, we generally see the same subscripts here. Again, the temperature is being recorded as to where this is happening, and we have our positives and our negatives. Vaporization, again, is looking from liquid to gas, but we can also use vaporization to go from gas to liquid. Just like in terms of fusion, the only difference that we have there is, again, our operators. So here, because we're going from liquid to gas has a lot more kinetic energy, so we need to add some energy into that. And again, here, from going from gas to liquid, a lot less kinetic energy in a liquid, we lose that as heat. And again, the thing that we're looking at is the enthalpy change when 1 mole of substance is converted from liquid to gas, and that's why we have this highlighted. So this value over here, the 40.7 kilojoules per mole, it's per mole of the H2O liquid. Okay, so that's the key, is that in this case, it doesn't really matter because the coefficient of this and this is the same. So you would get the same answer, but the meaning would be wrong. Okay, so again, you need to make sure that you're properly defining this value based on the proper definition that you're looking for. When we're looking at atomization, it's looking at 1 mole of gas atoms and converted from its elements under standard conditions. So when we look at here, now this is a little bit different because naturally, under standard conditions, chlorine is found as a gas and sodium is found as a metal, sodium metal. So we're turning them both into gas, Cl gas here and Na gas. So there will be some difference in energy. Now you can see it's not all that much, but the meaning is the same. So regardless of whether you start from a gas or a solid, you're turning these atoms into gas atoms. Again, here you found it in standard conditions as a molecule, and you're turning it into individual atoms, and there's a certain amount of energy associated with it. So again, pluses mean it's endothermic process. I need energy to convert from here into here, that's the positive, and I need 121 kilojoules for every mole of this created. So again, my coefficients in this would be 1 here and 1 over here. And that forces me to use a half over here. When we're talking about solutions or dissolutions, it's about when 1 mole of solid dissolves in a large excess of water, again under standard conditions. So in this case, we would have something like sodium hydroxide, which is a solid in the water, and we produce sodium hydroxide aqueous. So again, aqueous refers that this is dissolved in water. Okay? Now, this process is a little bit more complex than this. It looks at something called lattice enthalpy and also hydration enthalpy. So basically, the amount of energy to actually break the NaOH up, and then the amount of energy released when these Na and OHs combine with water to produce your Na and OHs. So this value is a little bit more complex, and as you can see here, you need energy to first break them up. You have separated particles, and then so here's your solvent, this would be your water, this is your solute, this would be like, for example, your NaOH or NaCl. They separate from one another, so in between here, there are ionic bonds. Here, there's hydrogen bonds, London dispersion forces. Those all require energy to break apart. When they form and they recombine, they release a certain amount of energy, and that change in energy between what was put in and taken out is our overall enthalpy of solution. And again, it's calculated by 1 mole of solid that dissolves, not how much is created, 1 mole of solid that dissolves. Now we get into the chemical enthalpies, and again, this is formation. This is one of the ones that we'll be using a lot in this course. It's the amount of energy, or the enthalpy change when 1 mole of compound is formed from its basic elements under standard condition. So here, when we have water, if we actually were to do this out and balance it properly, what we would have would be H2 gas plus O2 gas, and that would produce H2O liquid. Now again, one thing that you have to remember is that water, when we actually react this gas and this gas, initially gas water is formed, or steam is formed, but the energy is lost, and under standard condition it exists as a liquid, so we write it as a liquid. Now we have to balance this. We put a 2 in there and a 2 over here, and so there would be a certain amount of energy change with this. However, I want to get it into a standard enthalpy of formation. Standard meaning that, again, I have to account for the liquid, and the enthalpy of formation means I have to get in a per mole basis. So if we go back, this value was twice, the amount of enthalpy change from this reaction was twice as much as this one over here, but we took the 2 mole, we took that value over here, divided by 2 mole of the water being produced, and we get this value over here, and that would be the enthalpy of formation. Now, a big important note is this one over here, is that any element in its standard state is 0. So we don't really see it in this case over here, because we are actually using and breaking up that oxygen molecule and repurposing it into creating the water molecule. But there will be times when we actually have oxygen being used as a reactant and then formed. And so when this actually happens in the exact same states, so here we have gas, oxygen, oxygen, gas over here, the enthalpy change is 0. Okay, so again, it's 0. We don't have any enthalpy change from this going into here because it's not changing state, it's not changing configuration in terms of chemical reaction, and so the enthalpy change is in fact 0. This is a very, very important point to remember. We will see it a little bit later when we talk about enthalpy calculations. And combustion is another one that we're going to be using. It's when 1 mole of compound is completely burned in oxygen under standard conditions. So again, if we look at this reaction here under standard conditions, we would produce liquid water, and we produce CO2 gas, O2 gas, and methane. All of these exist in their proper states at standard conditions. Now, luckily for us, this balanced equation is already balanced with the coefficient of CH4 having number 1. That means I don't really have to modify anything else. If this was a coefficient of number 2, the CH4, I'd have to adjust all the other ones so that this one would have a coefficient of number 1. So again, here what we have is this number over here. The negative represents that heat is being lost, aka the enthalpy is decreasing. So in this case, again, what we'll have is that these ones will break apart. The O2, the CH4 will break apart. They'll get rearranged and they'll form CO2 and H2O. In that case, the amount of energy that was put in is less than the amount of energy that was released, and overall this would be an exothermic reaction. So 890.7 kilojoules is released for every mole of methane burned. And finally, neutralization is just the same. It's again a chemical reaction, and we look at the number of water molecules formed. Now, this one is a little bit iffy because some textbooks say a little bit differently. For the purpose of this course, we're going to be using 1 mole of water being created. And again, so this value for every mole of water created from this neutralization reaction, again, this is a base, this is an acid, hydrochloric acid, and sodium hydroxide, produce a aqueous salt and water, and 58 kilojoules of energy will be released for every mole of water being produced. Okay. Now, sometimes you will see this one. This is called the standard enthalpy of reactions, denoted by sub R over here, and this is just showing you in the quantities actually shown. So again, going back to our water example here, when we were looking at delta H of formation, we had to get this coefficient top of the water to 1, because it's the amount of energy released for every 1 mole of product being formed, which means that I had to have 1 mole of H2 and I needed to half a mole of O2. However, sometimes they just want to state it as this, so if they want to put it into a standard enthalpy, you'd have it in per mole basis of your reaction conditions as is. So you could choose any one of these, so you could say 2 moles of that, 1 moles of that, 2 moles of that. You could divide this value by, or the value that you get, by any of those, and you should get the same answer. Okay. Now it's a little bit hard to see here where you say, oh wait, I have 2, 1. If I divide some number by 2, I will get a different number if I divide it by 1. That is true, but the value that you get depends on what you're measuring over here. So we won't see that very often, but that is what that means over here. Most of the times, if they want to show the amount of enthalpy change in the values stated, all it will simply do would be delta H without any subscript, and that would be just as is over here. Now, a little hidden problem over here, and it's not something that we need to know at this level, but just because you might be thinking about this. If we had hydrogen and oxygen, if you ever put those two gases into a balloon, you know that they don't react. You need an ignition source to react. And so, as a result, when you do this, you get a huge, massive explosion that acts as a fuel for the rest of these molecules to react with one another. So you need a pretty big ignition source from that, and they react at a very, very, very high temperature. However, the value that we have over here is quoted for standard reaction conditions. But again, hydrogen and oxygen don't react under these standard conditions. So whenever a standard enthalpy change is quoted, the standard conditions are actually assumed. If the reaction has to be done under different conditions, a different enthalpy change would be recorded. And this is, for example, like this one. This doesn't happen at 298 Kelvin, aka room temperature. It happens at a very much higher temperature. And so a different enthalpy change would be recorded. And what that has to be done in more advanced chemistry is that you'd have to calculate back to what it would be under standard conditions. So again, we don't have to do this at this level, but just something that you might be thinking about as we go through this example. And finally over here, if you had a reversible reaction, and we're going to be talking about this dynamic equilibrium a little bit later, what we can see is that here this shows the equilibrium reaction. That means that these reactants turn to products, and the products also revert back to the reactants and back and forth until they find a happy balance. What you can see that if this reaction occurs in the forward direction, going from left to right like we normally see, we'd see that this has a negative sign and it releases 92 kilojoules for every mole of NH3 formed. Now in this case, it's actually not a delta H of formation, it's just a delta H of reaction. So this value relates to these coefficients that we have over here. However, the important point is that if we actually switch the reaction, or we read it the opposite way, so this ammonia is breaking down into nitrogen and hydrogen, what that does is that the sign of the enthalpy changes. So the key thing here is that if the direction of the reaction is reversed, the sign of the enthalpy reverses as well. Here, energy is being lost. Here, energy is being absorbed. Thanks very much for watching. See you in the next episode.